Gennady received his PhD in theoretical physics from St. Petersburg University in Russia and came to the United States as a postdoc. And I guess the first time I met him, I think, was in 2011 or 2012 while he was doing a postdoc with Alex Nymart at Rutgers. And I really enjoy interacting with Dr. Gor. He's a very talented scientist with a lot of enthusiasm for research. And I think that you'll feel that enthusiasm coming through in his presentation. He is an expert in modeling, and he's particularly has interest in porous material and phase behavior in porous material. I think this is a great match for a lot of the research topics going on at KU, which is another reason why I was excited to bring him to present here, both in our petroleum colleagues, but also in chemical engineering, where we use porous media for everything from separations to catalysis. So, Dr. Gor.
All right, thank you, Alan, for your introduction. Let me share my screen and please confirm that it's all visible. Let me go to the full screen mode. So everything is seen. Excellent. All right. Once again, thank you. It's a great pleasure to have these opportunities speaking in front of your department graduate students and faculty members. I wish it were taking place in person, but it is what it is, right? So I'm going to talk today about compressibility of subcritical and supercritical fluids confined in nanopores. But before I go in details of research, I just wanted to quickly give an overview of some other projects I work on. And
hello.
Yes, am I heard well? Okay.
You're coming through clearly. I'm not sure who that speaker was, but please continue.
Oh, sure. So my group is called Computational Laboratory for Porous Materials, and it doesn't mean that I only work on porous materials. In fact, we work on a number of problems related to fluids at interfaces, while fluids in confinement, and yes, porous materials in particular. And one of the projects, which I'm not going to go in too much details, but this is the project which was recently funded by NSF with a NSF Career Award, is work on smart porous materials, on stimuli responsive porous materials. And I know showing a picture of a pine cone, well, doesn't probably make an image of a very smart porous material, but in fact, this pine cone is made of nanoporous silica, and it behaves similar to a real pine cone. It, when you change the humidity, it opens and closes. So it has these mechanical response to the adsorption of humidity. And I'm working on a theory of this phenomenon known as adsorption-induced deformation. So another area which I'm working on is on developing toothpastes, and I just recently got a grant from Colgate. I'm not unfortunately allowed to speak much about the details of this project, but we're trying to look from the molecular perspective on some of the effects taking place in the dentin, which is also porous medium. Another area where I work is atmospheric soot. Atmospheric soot is not a nanoporous material, but it's a nanostructured particle. And these particles adsorb, or well, the vapors condense on the surface of these particles, and there are a lot of interesting physics and chemistry going on these interaction of the soot particles with condensing vapors. And last but not least, it's I work on properties of porous polymers, and in particular the porous polymers which are used as components of lithium-ion batteries. But today the focus is on compressibility of the fluids in the nanoporous media. So the motivation for this work is, while mainly coming from petroleum field. So in recent years, there has been a lot of effort towards exploration and development of unconventional hydrocarbons, shale gas and shale oil. And one of the key differences with conventional hydrocarbons in that is that the media which consists them is nanoporous. So it's nanoporous media where the hydrocarbons are often in these confined or adsorbed state. And I'm just showing a couple of pictures of shales with the pores in the nanometer range. So when fluids are confined to tiny pores, many of their properties change. And I'd like to mention just a few effects of the confinement, and in particular, one thing which probably many of you are familiar, and well, certainly Dr. Algar is very familiar, is the phenomenon of capillary condensation. So if I take nitrogen at normal boiling point, and by the way, to make sure you guys are not asleep, could you type in the chat what would be the normal boiling point of nitrogen, if you remember? The wrong answers count as well. So if I take nitrogen and its normal boiling point, if it's in bulk, right, at this temperature, the normal boiling point means 1 bar. But if I look at nitrogen at the same temperature and yeah, at the same temperature, and I got a bunch of right answers. That's terrific. Thank you. So if I take nitrogen at 77 Kelvin and look at its condensation in the pores, the condensation will take place at much lower pressure, which is called capillary condensation. So the phase transition is taken at the different pressure here. Moreover, this pressure is used for characterization of porous materials. This point of capillary condensation is a fingerprint for to get the pore size or pore size distribution. So another example, also not a very exotic example, this has been known for years, that the other type of phase transition, freezing in the pores, take place at a different temperature, right? If you look at freezing of water in the pores, if you look at the endotherms, you will have these peaks way below the 0 degrees centigrade. Well, it's not only the temperatures or pressures of the phase transition, but properties like thermal expansion, for example. These properties would be also affected by the confinement. Unfortunately, this is grayscale image, but the bottom line here is the thermal expansion coefficient of the bulk water, and the lines above it are the thermal expansion coefficients of water in the pores. So many properties of the fluids are affected by confinement. And here I want to address the main question. So does confinement affect compressibility of a fluid? And well, another question, how one can measure experimentally or predict theoretically the compressibility of a confined fluid. So before getting into, well, talking about molecular simulation and other things, I want to talk a little bit about experiments, and in particular experiments related to wave propagation in porous media. And the reason is the following. So waves are used in geophysics for many purposes, for characterization of geological formations, for characterization of rock samples. And there are two types of waves which are depicted in these cartoons: the P waves or longitudinal waves, and the S waves or transverse waves. And they're different in, well, I think this cartoon does a very good job showing what's the difference between them. So the longitudinal waves are related to the elastic property called longitudinal modulus, and the longitudinal modulus M is can be calculated from the density of the sample times the squared velocity of these waves. Similar with the transverse waves, where we have shear modulus G, and it's related to the corresponding velocity with the same type of equation. So things are a little bit more complicated when we get to porous medium. and in particular porous media saturated with something else. So it's a composite material. So I'll be talking about the properties of the composite. Along with the longitudinal and shear modulus, I will also be talking about the bulk modulus or hydrostatic modulus, which is can be related to the other two moduli of these equation 3. So I will introduce the notations in this figure because I will need to use them in the further slides. So there could be moduli related to different parts in these composites. So first, it's the K naught would be the bulk modulus of the dry porous sample. Ks would be the bulk modulus of the solid constituent of the pore wall, if you wish. And Kf would be the modulus of the fluid inside these pores. And K without any subscripts would be the modulus of the composite, of the solid filled with the fluid. So, of course, these topic that the studies of porous media, conventional porous media, macroscopic porous media, it's an old topic. It's been studied for decades, and there are some theories written to relate the properties of these composite to the properties of its constituents. And in particular, well, we know that the fluid doesn't have a shear modulus, so if pores are filled with fluid, the shear modulus of the composite is the same as of the dry material, and the bulk modulus can be calculated with a pretty simple equation, which is called Gassmann equation, and it is in fact a low frequency limit of Biot theory, so often called as Gassmann-Biot equation or Biot-Gassmann equation. So here, in addition to the terms I introduced previously, there is one more term, which is phi, which is the porosity, the fraction of voids in the sample. But in any case, it's a very simple equation. If we know properties of the constituent, we should be able to predict the modulus of the fluid saturated porous sample, and therefore to predict the velocities of wave propagation in it. So it could be written in terms of the longitudinal modulus. And of course, the concern is that it has been derived for the classical macroporous media. And the question is, does it work for nanoporous media? And that's the question I'm going to be addressing in the next several slides. So again, a little bit more about experiments, although I haven't done these experiments myself. These are quite old experiments, but in order to appreciate the results I will be showing later, some details are needed. So gas adsorption is, well, Dr. Alger can confirm that it's a very routine technique in particular for characterization of porous materials. So in order to look at gas adsorption, you can just enclose your sample in a certain container, control the temperature, so have the temperature constant, and change the vapor pressure, and add a little bit of your gas or vapor in the system, and see how the mass or well, other parameters of the sample change, so volumetric or gravimetric measurements. So in addition to that, you can, with the same sample and with well, a setup which is just slightly more complicated, you can actually look at how adsorption of fluids in the pore space, how it affects the wave propagation. So in order to do that, you just need to attach a couple of ultrasonic transducers to your sample and generate an ultrasonic pulse and measure the time it takes for the pulse to go through the sample with an oscilloscope. And from the time, from this time, you get the, well, and knowing the geometry of the sample, you can get the velocity. And you can do it in situ during the adsorption experiment. And this has been done first, well, to my knowledge, first time with a nanoporous sample back in the late 80s by Warner and Beamish. And they got quite interesting results on how, well, on the, essentially on the elastic properties, on the moduli of Vycor glass, on nanoporous glass sample during, as a result of these experiments. So let me start from, I'm showing their data. I'm showing these data from the 1988 paper, but I'll give some comments on, well, more recent works on that. So first thing to measure is an adsorption isotherm, and it's measured here by volumetric technique. The adsorption isotherm, it's the amount adsorbed as a function of vapor pressure. And for many nanopores, or better to say mesoporous materials, so the pores are on the order of several nanometers wide, the adsorption isotherms look like this one. So initially we have some fluid adsorbed on pore walls, and then when the pressure goes further, we see these capillary condensation effect I was mentioning before. So the pores, the condensation takes place. The pores get filled with the condensate, with the liquid-like stuff. And here at the top, well, the pores are pretty much filled, and it's only like small meniscus at the pore entrance, which would be remaining. So they measured the adsorption isotherm, which is a routine thing. In addition to that, they measured these velocities, the longitudinal and transverse velocities of the wave propagation in the sample during the adsorption experiment. So as a function of relative vapor pressure. And these are their curves from their paper. So if, well, and they for whatever reason, they didn't report these data, but I was curious enough. While we looked at the moduli of their samples, so we calculated the relative change of the shear modulus, which I can easily calculate from the velocity and the amount adsorbed, which gives me the density. And the shear modulus pretty much does not change during these experiments. There is slight deviation, but overall it's almost not changing. The green line is showing just the zero, so what's we expecting it to be. More interesting would be to look at the longitudinal modulus. As a longitudinal modulus, and I show here the results of, it's two ways to calculate it, and I'm not going to go in details unless you ask me in the end, but they give pretty consistent results with just slight constant shift between them. So if we look at the longitudinal modulus, it looks quite interesting. Initially, while it's mostly, the relative change is mostly zero, it's mostly not changing. So here in this region, on the region before the capillary condensation, so till pressures reach, let's say 0.8, relative pressure 0.8, the modulus is pretty much not changing, just decreasing a little bit here prior to that. And then it changes abruptly. And after that, it changes, well, you can say it changes a little bit. It's not, it doesn't stay constant, but it's increasing a little bit. Well, I want to emphasize that later, the same type of experiments were repeated for different fluids for similar samples. Again, it's nanoporous Vycor glass, and here is the longitudinal modulus of the sample as a function of the relative pressure of argon at normal boiling temperature, right? Again, it's flat, it's not changing. And the longitudinal modulus shows the same behavior with no change initially, and then abrupt increase and a slight increase at the end. And also here, unlike the previous slide, you see the desorption branch, which looks similar, except for it has a hysteresis, which is, well, obviously related to the hysteresis and the adsorption isotherm itself. So, and even more interesting is to look on these change of the modulus of a sample filled with liquid hexane, right? It's not changing initially, abrupt change, and then it continue increases. So here, these increase of the modulus is seen even better. So, well, the question, of course, looking at these data, what is going on, and are we able to model these data with the Gassmann equation? Right, and what we did to begin with, well, that's we can take the K naught, the modulus of a dry sample, easily from the ultrasonic measurements on a dry sample. We can take Ks, the modulus of the solid constituent, which is a little bit tricky because it's hard to probe the pore walls, the elastic properties of the pore walls, but we came up with an approach to do it. And then we take the modulus of the bulk fluid, the porosity, and predict the overall, the modulus of the composite, or the longitudinal modulus. And this is what we got. The predictions is this flat line, right? This is, I'm not showing anything before that, because here it's clearly zero, and it would be just like a Heaviside function, essentially. So here, here we have this line, which is quite close to experimental data, but it's constant. It's flat, right? It's not changing. And if I show you the data for argon and hexane, it would be even more clearly seen, except for here we have the two lines for the predictions, because we used two different ways to calculate the modulus of the solid constituent of the pore walls. And in any case, obviously the Gassmann equation, you plug in the constants, you get the constant. So here you have the constant, although experiments clearly show even when the pores are filled with capillary condensate, the modulus keeps changing, and these changes quite significant, especially for these hexanes. So there is a clear mismatch between that, and well, one of my goals was to understand where these mismatch is coming from and whether we can actually get some agreement with the experiments. So in order to do that, we need to calculate the fluid modulus somehow from molecular simulations. And well, the first disclaimer I need to make is that the moduli probed in ultrasonic experiments are more likely to be adiabatic moduli, and in simulations it's easier to calculate the isothermal moduli, and we can relate the two through the heat capacity ratio. And then I will also hear some of the formulas are given in terms of the compressibility, which I think, unlike for me, where they deal with in thermodynamics, we typically deal with compressibility. So, but compressibility is isothermal compressibility is just the reciprocal for the isothermal modulus. By definition, the compressibility, the isothermal compressibility, is given by this partial derivative, right? Volume and pressure. And statistical mechanics gives a recipe to calculate, and not only it, but other derivative thermodynamic properties can be calculated from the fluctuations of different thermodynamic properties in various ensembles. And in particular, the compressibility can be obtained from the fluctuations of number of molecules in the grand canonical ensemble. So when the chemical potential, volume, and temperature are constant. And I want to say, of course, these equation, OpenAI StatMech book, it is derived assuming the bulk fluid. Nevertheless, this equation is widely used, and I put several references here for predicting the compressibility of fluids in confinement, and I did this as well. So the model here, and then this is why I specifically like the problem with nitrogen adsorption, because nitrogen is very simple, especially when nitrogen is interacting with something like silica. The interactions are mostly non-specific. It's a Lennard-Jones. They can be represented by Lennard-Jones potential, and this is done routinely. Calculation of adsorption of nitrogen in silica or in porous glass has been done for many years. So I take the known potentials, I take the Lennard-Jones parameters for nitrogen interaction, for nitrogen silica interactions. I use the Monte Carlo simulation in the grand canonical ensemble. I'm not going to go in details, but if you'd like to, I'd be happy to explain the method in more details. And the only, well, I'm doing what people typically do to predict adsorption isotherm. The only thing I do differently, I run my simulations while a couple of orders of magnitude longer than typically, because in addition to calculate the number of particles in the pore, the adsorption isotherms, I need to calculate the fluctuation of these property. And I'm just showing here the parameters. I want to emphasize, I don't tune any of the parameters for my simulations. I take them from the literature. So the first results would be adsorption isotherms. And this is, well, nothing interesting. This is well known. If we take a pore of a certain geometry, and we focused on spherical pores. We tried cylindrical pores and it worked as well, but with spherical pores, it's somewhat easier to work. And we calculated isotherms in the pores of different sizes, ranging from 2 nanometers to 8 nanometers. This is how they look, right? And for each point on these isotherms, given by a number of particles in the pore, we look at the variance of these number of particles. We look at the fluctuations, and from these fluctuations, we calculated compressibility or the elastic modulus. So this plot shows the elastic moduli calculated from these adsorption isotherms for different pore sizes. Different colors are different pore sizes. We also use 2 different methods to calculate them. This is why there are 2 lines of each color. Again, don't want to go in too much detail. One important line on this slide is these black dashed line here at the bottom. This line shows the modulus of bulk liquid nitrogen at normal boiling temperature of 77 Kelvin. So the moduli of my nitrogen in the pores, these moduli exceed the modulus of the bulk liquid nitrogen everywhere. It's and especially at the saturation point here. So these lines look much better if I plot them in logarithmic scale, or if I plot them as in this picture, I plot them as a function of the Laplace pressure, the capillary pressure in the pore. And so you can see that the moduli of the liquid nitrogen in the pores is changing, and it's changing linear with the Laplace pressure. Well, of course, the nice thing to do is to take the pore corresponding to our Vycor glass, and Vycor has the pores of the size roughly 7-8 nanometers. Plug these data into Gassmann equation, which I announced earlier, and compare it to the experimental data. And as you see, these points here, they ended up clearly right between the 2 different experimental curves, which we considered a very nice agreement. Where we have disagreement is with the capillary condensation point. And this is related primarily to the fact that we assumed spherical pores, which is not true for Vycor glass. So if a channel-like pores, if a cylindrical pores was taken into account, the capillary condensation point would be further to the right, closer to the experimental data. But overall, the agreement is quite nice, and it shows this increasing trend in the modulus. So the same, while we did comparison for argon and hexane, and it's beautiful. I think this agreement is just phenomenal. We got the right slope, and we got very close to these experimental curves. So it's not just unique to nitrogen. So what is even more interesting, and I think this is probably the most important plot in this presentation, is if we look at our modulus at pressure P equals to P naught. So when the pores are entirely filled with a capillary condensate, and we're at the normal, at the normal boiling point, right? If it's nitrogen at 77 K, we're at 1 bar of pressure. And we look at the modulus in these saturation case, right? And compare these points, which are plotted as a function of pore size. So at the top, these are the pore sizes. At the bottom, these are 1 divided by the pore sizes. So what we see is that the modulus is a linear function of one of the pore size. So the moduli for all the pore sizes, they always exceed the value of the bulk liquid, for the bulk liquid, this dotted line here. And furthermore, if we go to the pores as small as 2 nanometers, these difference would be roughly a factor of 3. So that's quite a substantial difference in the modulus. So we got the nice linear relation, and we got a significant effect with the modulus. So why is that happening? What's the mechanism? Why the modulus of the fluid is higher than in the pores is higher than in the bulk, or why the compressibility is lower, right? There could be 2 explanations. The first explanation is quite straightforward, and while it's microscopic, but I think it's very transparent. So if you think of adsorption of a fluid in your pore, your density profile would look something like this here, and this is the density profile. I think this is actually for argon. Yeah, that's from our earlier paper when we simulated argon. And you will have these density peak near the pore wall. So the pore wall here is at the point 0, right? So these density enhancement, of course, the more dense layers are stiffer. They have lower compressibility. They have higher modulus. So if you go to smaller pores, the contribution of these surface layers, the contribution of these dense layers to overall modulus will be higher. So these explains why in smaller pores the moduli are noticeably higher than in larger pores. Another explanation is more phenomenological, if you wish. So it is through the modulus pressure equation. So if we look at the pressure in the pores, and this is a topic I've been working on for quite a number of years. So these high pressure in the pores, which cause the deformation of nanoporous materials. So we call them salvation pressure, and it has 2 contributions from the solid liquid interactions and from the Laplace pressure, the capillary pressure due to the curved meniscus. So even when, well, if Laplace pressure is present, Laplace pressure is changing as log pressure, right? If it's absent, the solid liquid term will be proportional to 1 over the pore size. It scales like 1 over the pore size. So then there is this Tate-Murnaghan equation, an equation from, well, 1940s, which says that at high pressures, the modulus of a solid or a liquid as a function of pressure is roughly a linear function of the pressure. So it's not constant, but it's a linear function with a certain coefficient. And of course, well, if the pressure scales like 1 over the pore size, these 2 equations explain the linear relation to the reciprocal pore size. So before concluding, I want to show the data for supercritical methane. And this is, one of my students did this simulation. The idea was to verify, okay, how much the different models, the deviation from simple Lennard-Jones fluids would matter, and how much the supercritical, the fact that we look at the supercritical system, does it matter for the effects we're observing? So he looked at the methane, which is also, well, more relevant to the initial motivation of this work. So it's more interesting to those working with shale gas, right? So these data this is Lennard-Jones methane, and this is explicit hydrogen methane confined in a carbon pores, simple slit carbon pores. The reason we took these pores is we didn't want to reinvent the bicycle. We wanted to take the systems which have been simulated in the literature and calculate our elastic properties for those systems. And we took these isotherms, so the dashed lines, the lines here, the isotherms from the literature. It's simulated isotherms, and the points are the points which we obtained from our simulation. So we matched the isotherms, and then for each of the point on the isotherm, and here on each of the point, you see the error bars. Essentially, from these error bars, from these fluctuations, we calculated the moduli. And I'm showing just the final plot with the results. So the modulus of confined methane in the pores of different sizes. So zero reciprocal pore size, this point corresponds to the bulk methane. These points correspond to the methane in the pores of 2 nanometer wide. And while we see the same trend as we saw for nitrogen or argon, but the trend, in addition to the trend, the magnitude here is much bigger. So if you look at the modulus here and here, you can see that this is in fact a factor of 7 difference for the modulus. And also I want to emphasize the different, while there are a lot of information in this plot. So the different lines, the different points correspond to Monte Carlo and molecular dynamics simulation, and also to the united atom and explicit hydrogen models for methane, and they're all very, very consistent. So with that, I'm getting to the conclusion. So first, well, analysis of experimental data suggests that the longitudinal modulus of a confined fluid differs from the bulk. Well, along with some other properties I mentioned in the beginning, confinement affects the compressibility or the elastic properties. Then isothermal compressibility or modulus of a confined fluid can be calculated using GCMC and or MD molecular dynamics simulations. The modulus is found to be affected by the solvation pressure in the pores, and it changes logarithmically with the vapor pressure. It's a linear function of the reciprocal pore size for, well, all the different systems we simulated. And the results, which is consistent with the ultrasonic data on porous glasses saturated with nitrogen, argon, hexane. Well, I have to admit I have not seen similar data on supercritical methane. So the last part of this work, it doesn't have any comparison with experiments. So we can just say that, well, we predicted that the effects in supercritical methane are even stronger. And in particular, we have the 7-fold increase of the modulus in the pore sizes of 2 nanometers. And with that, I'd just like to thank you all for your attention. And I'd like to thank people who helped me in this work. Max Maximov, who is currently in his 4th year doing his PhD. Chris Dobrozhansky, who defended his PhD a few months ago. Nick Corrente, who was an undergraduate student in my lab, and now he's doing a PhD at Rutgers University, and Professor Boris Gurevich from Curtin University in Australia, who helped me to connect my nanoscale thermodynamics to his geophysics picture. Thank you very much.
So I'd like to say thank you to the speaker. That was a great presentation, and we have some moments for question. And if I understood correctly, Trung, I think I'm going to manage the question period through the chat box. So Dr. Gor, I trust you can have that chat box open. I think that for our students, we do welcome you if you like to read your question. If you like, you can turn your video on so that Dr. Gor can interact with you a little bit virtually. So Trung, did I get all that right? And would you like to ask the first question?
Sure. I have a question. At high fluid pressure, is it possible that the morphology or the structure of the porous medium could be affected? And if it's affected, won't it affect the modulus measurement coming from the porous medium by itself?
Mm-hmm. It's an excellent question. Thank you very much. Yes, in some cases. And actually here we need to talk specifically about the numbers, because if we look, and I would share a screen for a second, go back to these Tate-Mernigan equation. So which is a very simple idea. Okay, let me share it again. Okay, so this equation, so the modulus of a matter, right? Be it solid or fluid, whatever you want. So these modulus is constant it's a parameter for the material at very low pressures, but if your pressures are high, the modulus will be changing, right? And the pressure is high, it's changing linearly. If it's even higher, it can be, you can add quadratic terms and other terms here. So if your pressures are comparable to the modulus of your solid, right, then these effects you're talking about would have an effect. So let's say we're talking about silica. So the modulus for silica would be of the order of 70 GPa. So you would need a pressure of the order of 70 GPa to have an effect. Well, can you have these pressure due to these solvation effects in the pores? The answer is no. It's way too high. So the pressure would be in the range of, say, 10 MPa, and 10 MPa would not have much of an effect on the solid.
Yeah, I agree with that. You know, but there are a lot of porous media where the structure is not as rigid as silica.
Sure, that's why I said, well, we should look specifically on the modulus. So let's say if there is some soft components, like if some I don't know, polymers, or if you think of a natural porous media, if some organics or whatever, and the moduli are much lower, you would have these effects. Well, there could be, there could be plastic deformations as well, and in something which is more complicated than a nanoporous glass, there could be many of the well, funny effects. The effects beyond what I considered here so far.
Thank you.
Sure.
Dr. Gor, first of all, thank you very much for the presentation. I have a quick question. As you were talking about the solvation pressure or this fluid surface interactions, were you able to observe any enhanced interactions between a surface chemistry and a specific fluid, or whenever you change the fluid, you change the surface, see this parameter going down? Were you able to observe, or did you test something like that?
So correct me if I didn't, I hope I got it right. So you're asking whether if I consider different fluids which would interact differently with the surface, would that affect these pressure enhancement, right?
Correct, yes.
Yeah. Yeah, so certainly there is a significant difference depending on which fluid you take. So even if you replace your nitrogen with water vapor, the effects will be, everything would look different, right? The adsorption isotherm would look different. The forces, the deformation, these things would look different. Qualitatively, the effects I was talking about, they would probably be the same as long as liquid wets the surface. So if we have poor wetting, for example, imagine you have some hydrophobic surface and it's only some small clusters of water forming on these surface. It's not like a uniform coverage of the surface. Yeah, that will ruin the picture. But as long as you have good wetting, I'm sure in the fashion I predicted, the pressures and the moduli and so on, this can be predicted. And so far, we consider different fluids, and quality things were all consistent.
Okay, oh, thank you.
Thank you.
So I may ask a question that relates to the last one, because if we're thinking about the petroleum angle, we could have some of these gases adsorbed in inorganic materials, or we could have some of them adsorbed in that kerogen component, which is carbonaceous. And I was wondering if the strength of the interaction or that enthalpy only shifts the picture, which is what I heard in the response to the last question, or if it could have some more significant impact on on what you observe from the modeling. So even, is that enthalpy of adsorption important? Is it taken into the modeling, for instance?
Yeah, the enthalpy
Yep.
of adsorption, yeah, certainly. This, for example, one of the works we have done is we decided, all right, what if we just, in molecular simulation, we can just tune certain parameter and see how the picture will change. And we were tuning the energy for the solid fluid interaction, which is, well, not exactly, but almost the enthalpy of adsorption. And we saw how the effects were changing, and we saw that as long as the solid fluid interactions are favorable, as long as the fluid wets the surface well, we see roughly the same type of the effects, with the modulus. Yeah, if the wetting becomes poor, then yeah, you can have the opposite trend. You're in the solvophobic confinement, and I didn't mention any of these works here, but there were molecular modeling mostly works where people looked at the water in hydrophobic confinement, and one of the parameters they simulate is, oh, what's going on with the compressibility, and well, the effect is exactly the opposite as in the hydrophilic confinement. So yeah, it's a different, instead of the fluid in such confinement will, instead of being stiffer, it becomes softer.
Are there other questions from our audience? So given the time, I'm going to call it a wrap, and join me in thanking Dr. Gor. Some of you know that you can that reactions thing and give him a clap, but we really appreciate the seminar. I want to note that Dr. Gor did just receive this NSF Career Award, so I think there's lots of room for exciting stuff to be happening in his group going forward, and I think the potential is really high. So thank you very much. Thank you very much for having me. I wish I were there in person. If somebody would like, I would actually, one thing I miss with this format is an opportunity to meet with faculty members and maybe the students and to chat a little bit. So if somebody has something to discuss, just follow up with an email, and let's schedule a Zoom call, and I'd be more than happy to chat about potential collaborations and other things. Yeah, and if anybody prefers a group chat to lower the barrier for reaching out, I'm happy to coordinate it. If you just saw something that was interesting there and you only had one question, shoot me an email too, and maybe we can just have a group chat that could be friendly, and it doesn't have to be long, so don't feel inhibited. So thanks very much, everybody. We're going to sign off now and wish you all a great day. Thank you.
Thank you.
Bye.
Bye-bye.